Hello everyone, I'm Hesham Almatary. I work as a software engineer at Capabilities Limited, and today I'm going to talk about how to enhance seL4, C and C++ user space memory safety using CHERI. Just to give a bit of a background about me, I did my PhD, as Gernot said, at Cambridge. My PhD thesis was about CHERI compartmentalization for embedded systems. Before that, I worked for 2 years at the Trustworthy System Group. During this period, I added features like SMP and FPU to ARM and the RISC-V port. Today, I'm going to talk about 3 main parts: software security, why it's important. Then I will give an overview about CHERI and the solutions that it's trying to provide for software security, specifically memory safety and software compartmentalization. And then the main part of my talk is going to be about CHERI-seL4, a project that I have been working on, why we are doing that, how we are doing it, the progress so far, and next steps. So software security is important. We are narrowing down software security to 2 main subcategories, memory safety and software compartmentalization. Memory safety here is quite important. According to a recent Microsoft study, 70% of their software vulnerabilities in the Windows systems were memory safety related. So memory safety here is split into 2 subcategories even, spatial memory safety and temporary memory safety. So spatial memory safety, for example, if you have a buffer overflow, if you have an array of 10 objects and you are trying to access the 11th object, this is a buffer overflow. It shouldn't be allowed. Temporary memory safety is like control flow attacks, like double free or use after free attacks. And these kind of attacks are allowing exploits that touch confidentiality, integrity, and availability of the system. On the other hand, another software protection mechanism is software compartmentalization. So this basically means we can take a monolithic software system or project, we split it up into smaller compartments. If one compartment got compromised or is malicious, it doesn't affect the rest of the system. And this is assuming 0-day vulnerabilities, and it's dynamic when it comes to security. And this is what CHERI is trying to offer: memory safety and software compartmentalization. What is CHERI? It's a hardware-software capability system. It has been under development since 2010 at the University of Cambridge and SRI, and it has 3 main principles here: intentionality and least privilege, like most capability systems, including seL4, and most importantly, software and source code compatibility. So we don't want to rewrite everything in memory safe languages. If we have 100 or 1,000 lines of code project, we don't want to rewrite that. We have different prototypes for CHERI in terms of software. We have the tool chain, which is mainly LLVM. We have different operating systems, CHERI-BSD, which is a port of FreeBSD to CHERI. It's running on CHERI-RISC-V and Morello. We also have Morello Linux from ARM, and we have for embedded systems CHERI-FreeRTOS, which doesn't have MMU. There are different prototypes in terms of hardware and processors. This table includes what companies are releasing what processors. So from Cambridge and SRI, we have 3 main soft cores that can run on FPGA. Piccolo and Flute are mainly targeting embedded systems. They do have MMU, but ARM32 kind of systems. Tuba is an application-level processor. It's an out-of-order one, so it's on the same bar as Morello. From ARM, as you know, we have Morello, which is the first ASIC prototype of CHERI. And from Microsoft, there's CHERIot, and this is basically an IoT version. So this is hardware running on FPGA and software as well. And the main benefit from CHERIot is that it is designed and implemented from scratch with CHERI in mind. There is also an IBIX core, which is embedded system core from Google, And CODA SIP 700 family is also going to include CHERI support. And just one note here, we are likely going to see more like CHERI RISC-V cores way before we see ARM cores in production. So if you have your own 64-bit system, including hardware and software operating system, and you want to add CHERI to it, what does that mean? So first, you are teaching your hardware to differentiate between pointers and integers. Pointers now carry bounds and permissions. Pointers cannot be created out of thin air, so this is similar to unforgeability aspect of seL4. You have to create your pointers from other pointers. All of these guarantees are deterministic, so it makes perfect sense for real-time systems, and no guarantees rely on secrets. Basically, all of your memory accesses and instructions need to go through valid pointers. And this is how the pointer looks like. If you have your 64-bit register, say in RV64, RISC-V, you are going to extend that in hardware so that it can include permissions, metadata, or type, and bounds, and a validity bit. So this capability or pointer now points to an area of memory with base and like bounds, top bounds, with permissions. If you try to access anything beyond that, it's basically a security violation, a CHERI security violation. And the validity bit here, or tag bit, is like protecting the capability integrity and derivation. So basically, you cannot create pointers out of thin air. If you try to do that, or if you try to mess with your capability, the valid tag will be cleared. In terms of the stack that has to be changed to support CHERI, it includes all of the stack from the microarchitecture level, going through the ISA, the compiler tool chain, your firmware, your operating system, up to the application level. So for the hardware, we are doubling the register size to hold the metadata. We have new CHERI instructions with guarded manipulation. If you try to violate some of the CHERI security aspects, you are going to get hardware exceptions. And we have tagged memory for integrity. On the hardware part, on the software part, we have two main protection models: pointer safety, which is the main application of CHERI, and software compartmentalization. Pointer safety is split into two main modes for CHERI: hybrid mode. And in hybrid mode, if you are building or compiling your existing C application or system, you are keeping your pointers as integers. You are not extending anything, but you have the option to manually annotate specific pointers to be capabilities to have some security on those pointers. On the other hand, in pure cap mode, if you are building in that mode, basically you are having every pointer represented as a CHERI capability with base and bounds and permissions. So for memory safety, if you are a C programmer, application programmer, and you want to port your C program to entertain CHERI's memory safety, pure cap mode, you have to follow some CHERI-C guidelines. I'm not going to go over all of them, but the most important ones is that you cannot assume anymore that the size of the pointer is the same size as long, which is an integer. For provenance, if you are trying to create a pointer for an MMU region, you cannot do casting like that anymore. So you have to derive that from a previous pointer, or you have to ask a more privileged entity to create a pointer or a capability, CHERI capability for you for that. And in order to have like complete details of the CHERI-C and C++ like guidelines, there is here a document that you can refer to. For software compartmentalization, CHERI right now has different CHERI software compartmentalization models. This is one of them. It's called CompartOS. And basically, we have applied it to FreeRTOS. And this figure is AWS over-the-air update application from Amazon. It's running on FreeRTOS. And the vanilla system was like running in single address space. nothing is protected. You have all of these libraries from third parties. So you can have one from ARM, one from Intel, and another one from Amazon. And all of them are working together. So we have taken that. We have applied software compartmentalization into them. And basically, this means every library now is a CHERI compartment. So for example, if we have a vulnerability in the FreeRTOS TCP/IP stack, it can no longer affect the applications, the AWS Amazon application. So this can have like secrets or keys that should not be like attacked or stolen. So moving to the main part of the talk today, seL4. So seL4, as we know, it's a secure microkernel. It's formally verified. It gives isolation guarantees between different protection domains with separate address spaces. However, it does not give C and C++ memory safety guarantees at the user level. More specifically, it does not give guarantees within the single address space protection domain of seL4. So we have like here a scenario of a typical seL4 system. We have VMs, an OS personality or server, and a normal seL4 native thread. And here, thread 2 or like cannot spy on VM1. This is protected and guaranteed using seL4. The OS personality or kernel cannot spy on the VM and vice versa. However, we have two attack scenarios here. You have thread 2 working in the same address space as the seL4 libs. If seL4 libs has a software vulnerability, memory safety, thread 2 can take advantage of that and can trigger an attack or an exploit. Similarly, if you have your OS personality or server, which is split into different components, but still they are working in the same address space, you can have your TCP/IP stack that has a vulnerability, and a device driver can take advantage of that, and vice versa. seL4 does not protect against that. And this is why we are trying to have CHERI and seL4. So we have seL4, which is great for providing some isolation guarantees using formal verification between different protection domain and different address spaces. CHERI is great hardware-software mechanism for providing memory safety and software compartmentalization within the single address space. And what we are trying to do here is having a CHERI-seL4 system, and we're trying to understand what does that mean. This is an underexplored design space, and we are trying to achieve something like that. We are trying to combine both technologies to entertain inter-address space isolation guarantees from seL4 and memory safety and software compartmentalization within a single address space using CHERI. This should enhance the overall system security, single address space and multiple address spaces, and in turn it also reduces the attack vector and protect lives and infrastructures and like sensitive data. So taking the previous figure we have from the current existing seL4 based projects, we want to take that and we want to like reduce these attack vectors here using CHERI. So we take that, we add support for CHERI for user space in the kernel and user space by applying software compartmentalization and memory safety. And here, this one is now protecting using CHERI. You cannot have memory safety attacks here anymore. If you try to do this attack, you will trigger hardware exception and a CHERI fault, basically. This is another example here. If you're in a unikernel, which is working in a single address space, you take it and you apply some software compartmentalization model, say compartOS that I discussed before, and you have your TCP/IP isolated as a compartment, CHERI compartment, and you have your device drivers isolated as a CHERI compartment. Now you cannot do this attack anymore. CHERI compartmentalization security, and memory safety will deny you this. And this is the ideal goal. This is not what we have right now, but we want to have everything pure cap. And I want to focus here that we want to have VMs that could be Cherry Linux, which is completely pure cap. Everything, including the kernel, libraries, and applications, are pure cap, completely memory safe, not rewritten in any memory safe language. And this includes relying on the VMM. This is also memory safe. So you also have some guarantees on the VMM, and basically are increasing the overall security of the system. This is the approach and goals of CHERI-seL4. This slide is mainly for verification people to make them less scared. So the ideal goal here from CHERI-seL4, we want to have a Cherry shared unified kernel and code base. Ideally, we don't want to do any forks. And we want to have just one flag to turn Cherry on, Cherry support on and off. So when Cherry is turned off, we want to this to be as close as possible to upstream seL4 right now without any knowledge of Cherry. So we want to maintain all of the seL4 existing guarantees, hopefully without any effects on verification, or no effects, or minimal or to no effects. This should not break any non-Cherry builds or tests. And basically all of the Cherry code that we have added is hidden behind like fdefs, Cherry fdefs. And these are not getting to be compiled when we are turning Cherry off. For Cherry code, this is going to be affected a little bit, but basically all of the shared code is going to be just renaming, code cleanup, and parameterization. So for example, we are not hard coding the register size anymore. We are having a macro. So instead of it's 8, we are going to have it like, say, register size, and depending if it's Cherry enabled or not, this is going to be 8 or 16. Similarly, we have like some renaming for the pointers. So current Cherry code is mixing the use of word t, which is an integer, and pointer t, which is supposed to be referring to kernel pointers. So we want to make sure for intentionality that all of the kernel pointers now are going to be pptrt, even though if Cherry is off, it's going to still be integer. But when Cherry is on, it's going to be a capability. And I would argue that when Cherry is off, even like with some of the verification that might get touched, you will lower your kernel to the same API, same performance, it's not going to be affected, and same types and sizes, and same output binary. On the other hand, when you are turning like Cherry for seL4, you will not bypass or trigger any privilege escalation for seL4. So Cherry will not give you any extra powers. This is not going to be verified, so it's expected to break verification, but it also can be verified in the future. It will also give you immediate guarantees to port your application to PureCap. So you will be able to entertain complete spatial memory safety for your existing C and C++ application in user space. And we are aiming to make this feature rich, including memory safety and software compartmentalization, with very minimum changes to the API or no changes, and a new API for Cherry, which is PureCap. This is what we are trying to achieve. So this is like what you should expect from us, what we are trying to do. This is still research, system research. It's design space exploration. We are trying to implement what we think is right from Cherry's perspective, and we're trying to understand what is actually right and how we can combine both technologies. We are trying to do that while following seL4 philosophy of just providing the mechanism and offload all of the security for Cherry to seL4 user space. And we're trying to do all of that using a flexible and generic clean design in order to like be as usable as possible give as many features as possible, and this should be the base for like future R&D projects that can be built on top. So I want to emphasize this has the feasibility and usability as the main goals of this project. So what does it mean when we have CHERI on? This is split into two main parts, hybrid and pure cap. But before that, I want to stress that we are going to have the user space always ported to pure cap mode. So it's going to be completely spatially memory safe. We are not going to support hybrid for user space. But the kernel could be built in hybrid mode or pure cap mode. And there are shared parts between both. So in hybrid mode, the kernel pointers are still integers. We haven't changed that to CHERI capabilities. So this is word T and seL4. This should yield in relatively minimum changes in the kernel itself. And this is not going to change seL4 capability representation, even though it does include some pointers. This is likely going to break verification, but it's not going to break it as much as pure cap. On the other hand, if we have pure cap here, we are going to maintain some functional correctness of the API and like API compatibility of seL4 and use cases. We are going to change the seL4 capability representation because now each pointer and every pointer is represented as a CHERI capability. So this is doubled in size and changed in representation. And we expect that this is going to like break verification significantly. We are also like, from CHERI perspective, this is going to be easier to port because according to our experience, porting to pure cap, porting software to pure cap, including kernels and user space, is easier than porting hybrid to CHERI. The shared parts here are mainly what is exposed and exported to the user. So this is every pointer in user space. This includes libseL4, which is the interface between the kernel and seL4 user space. So if there are any pointers here, they have to be converted to CHERI capabilities. The IPC buffer has to also change to be able to include at least capability size, not necessarily the tags, but at least the size and types. Register context here have to be saved as CHERI capabilities, even though they can just be integers, but they have to be of CHERI type. And we are doing also some CHERI hardware initialization at kernel boot. What we are adding in terms of the API or changing is new CHERI fault message. So if your user space now has a CHERI security violation, this is going to be exported to the user using a new CHERI fault format. And we are also going to export new PTE bits, page table bits for CHERI to user space, and this is helping with revocation, CHERI revocation, and probably like not being able to propagate some CHERI tag bits between different protection domains. So in terms of progress, now we have complete all pure cap seL4 test running and passing all the tests. So on the right hand side here, this is seL4 test passing like all the tests, and this is all in pure cap. This includes three main subsystems: the firmware, the seL4 kernel, and user space. For the firmware, the ELF loader, we have it like optionally. It can be compiled in pure cap mode for some targets or hybrid mode, but it basically has to enable being able to save CHERI capabilities and initialize some hardware bits. For CHERI-5, we have OpenSBI. This could be built in pure cap mode, but we don't have this right now. We have BBL, which is like RISC-V PK proxy kernel running in pure cap mode, so we can probably use that for seL4 in the future as well. But for now, it's just a hybrid, and it's basically, we have added support to be able to save and preserve cherry tags on traps. For the kernels, the progress here is that we have submitted a pull request and RFC to support generic Cherry seL4. This includes CHERI-5 and Morello. CHERI-5 includes RV32 and RV64. And for Morello, we have added 4 new platforms and targets. We have also submitted them. This includes vanilla Morello, and also it will support Cherry Morello. This includes KMU, FVP, Beehive, which is the KVM version of FreeBSD, and the actual Morello board, which is the hardware board. This is only pure cap kernel so far. We haven't added hybrid yet, and this includes the shared bits that I have discussed in the previous slides as well. We are going to submit also hybrid kernel in the future. And this basically enables building and running complete pure cap user space libraries and applications and servers. And this is a user space. We have ported seL4, seL4 test, which includes all of the libraries that it relies on, and seL4 bench as well. They get built and run in pure cap mode on hardware on all of these targets, and they pass all the tests. In terms of remaining work for this project, so this is like a 2-year project. What we have done so far is like 1 year. In the remaining year, we are going to add hybrid kernel support. We are going to have some benchmarking to differentiate and compare against the difference between pure cap, hybrid kernel, and compare that against vanilla Arch64 without Cherry support at all. We are also going to release all of the pure cap user space and firmware we have right now, and we are going to release some documentation so that people can reuse that, and if they want to reproduce it and build on top, they can do that. What can be done after this project? These are features that we haven't supported so far. So hypervisor support, MCS and SMP. We basically have supported Cherry for the default seL4 test configuration, which doesn't have any of that. We would like to also add some Cherry temporary safety support and software compartmentalization, and maybe we can add and port some other projects, existing C and C++ projects on top of CHERI-seL4. So for example, MicroKit, Lions OS, or unikernels and Unicraft running on a single address space. This gets us to the conclusion. So CHERI-seL4 is aiming to combine both technologies. We have shown that this is possible and feasible by porting it to a seL4 test and passing all the tests. This is still work in progress. We would love to get your feedback on top of that, and any help would be appreciated. And we want to make that very useful for both the seL4 community and Cherry community at the same time. I'd like to thank the Cherry group for making me reuse some of their slides, and also Trusted ST, MCA, SED, CodaSIP, and the seL4 Foundation for the discussions and collaboration we have had so far. So thank you very much. If you have any questions.
Well, we're having questions. Where's Caitlin? Can you just start setting up, please? Questions for Hesham? Ken?
More of a practical question. What are the hardware options for someone who wants to, use Cherry?
So yeah.
Well, the question was, what are the hardware options?
So
can you just disconnect here? So
yeah. So you have FPGA. You have FPGA soft cores. So Piccolo, Flute, and Tuba are soft cores that you can get and run right now on your FPGA. You have also Chariot. So Low-Risk is a company that started to release some FPGA board on top of that. Morello, you can apply for a Morello board. this is like limited in numbers, but you can still apply. Or you can wait for ASIC chips from Codasip and Google. In terms of simulators, we have QEMU, FVP. You can run.
Question was about hardware. So.
So yeah,